All right, guys, so we are going to pick up where we left off in the notes. So with example 9.2, using the impulse momentum theorem. So a ball with a mass of 0.25 kilograms is rolling to the right at 1.3 meters per second and then rebounds to the left, so again in the opposite direction, which means opposite sign, at 1.1 meters per second. So we are going to calculate the change in momentum of the ball and the impulse delivered to the ball. All right, so let's start by writing down some of our givens. The mass of the ball is 0.25 kilograms. The initial velocity moving to the right is a positive 1.3 meters per second. And the final velocity moving to the left is a negative 1.1 meters per second. All right, so now our equation for the change in momentum, delta P equals mv final minus mv initial. So I'm going to just factor out the m so that I don't have to keep writing it out. So it's just m times v final minus v initial. All right, so filling in my givens, I have that my change in momentum is equal to 0.25 kilograms times v final minus v initial. So negative 1.1 meters per second minus 1.3 meters per second. All right, so I do all my math and I end up with my change in momentum is equal to negative 0.6 kilograms times meters per second. So the next part of this question asks, what is the impulse delivered to the ball? And we know impulse is equal to change in momentum. So therefore, my impulse is also equal to negative 0.6 kilograms times meters per second. All right, so moving on with our notes. All right, so the impulse momentum theorem tells us that the average force is going to be inversely proportional to the duration of the time of the collision. So as we saw earlier, we can have a large amount of force that's exerted on the object for a very short period of time, or we can have a very small amount of force that's exerted on the object for a longer period of time. So inversely proportional, meaning a small force with a large time, or a large force with a small time to impart the same change in momentum on an object. Okay, you can read through some of these different examples. Here we have a 0.5 kilogram hockey puck sliding to the right at 10 meters per second. It's hit with a hockey stick that exerts the force shown, so we want to know what is the approximate final speed. So anytime we see a graph, we know that a graph of force versus time, that we're able to find impulse by finding the area under the curve. Now this curve is in a basic shape like a triangle or a rectangle, so therefore we're going to approximate the average force to be 25 newtons, and we know that the time period was from 10 milliseconds to 30 milliseconds, giving us a delta T of 20 milliseconds. All right, so the area under the curve in this case is going to be J, which is our area impulse, is equal to, like we said, 25 newtons, half of the maximum, divided by, or multiplied by 20 milliseconds. So moving the decimal place 3 places to the left, we get 0.02 seconds. So we get an impulse of 0.5 newtons times seconds. Okay, so now we know that impulse is also equal to our change in momentum. So m v final minus v initial. So using my impulse that I found earlier, 0.5 newtons times seconds, I set it equal to the mass, 0.5 kilograms, times v final minus v initial. Now v final is our unknown, minus v initial, which is a positive 10 meters per second. And we end up solving for v final to be equals a positive 11 meters per second. Okay, so continuing to move forward. I don't know why it's not doing it. All right. So, quick check. A light plastic cart and a heavy steel cart are both pushed with the same force of 1 second, and they're both starting from rest. So after the force is removed, the momentum of the light cart will be blank that of the heavy steel cart. Do you believe it will be greater than, equal to, less than, or you can't say? So looking at this, we think that change in momentum is equal to the impulse delivered to the cart. So if impulse is force times change in time, both carts had the same force delivered over the same period of time. They both all started from rest. So if the same impulse was delivered, they're going to have the same change in momentum. Therefore, their final momentum must be equal. So our answer is going to be equal to. Now, if you were thinking that the heavier cart was going to have a lesser momentum, you're right that the heavier cart would have a lesser velocity, but we're just looking for the total momentum after the impulse was delivered. The water balloon catch is similar to what we did today with the egg toss, that we want to have a larger period of time for the impact to take place over if we want to reduce the amount of force acting on the object. Okay, total momentum here is just saying that the total momentum, you have to consider all objects in the system. So you'll have to add them like vectors in order to find the net or total momentum of the system. And we'll apply this later in the chapter. All right, so let's solve a few more examples together. We always want to sketch the situation, define our variables, list anything we know, what's unknown, and then move forward with our problem from there. So looking at this next problem, I have a 150-gram baseball thrown with a speed of 20 meters per second. It's hit straight back towards the pitcher at a speed of 40 meters per second. So I want to know what is the maximum force that the bat exerts on the ball and what is the average force. Okay, so there we go. All right, so the mass of the ball is 150 grams, but make sure we convert that to our standard units. So moving the decimal place 3 places to the left, I get 0.15 kilograms. The ball was pitched in one direction, we'll say in the positive direction, so the initial velocity is 20 meters per second, and it's returned in the opposite direction, so that the final velocity has to have the opposite sign at a negative 40 meters per second. Now, it doesn't matter which of these you make positive and which you make negative, as long as they have signs that are opposite to one another. Now, filling it into our impulse momentum equation, I have delta P equals m v final minus v initial, which is equal to 0.15 kilograms times negative 40 meters per second minus 20 meters per second. So I find a change in momentum of negative 9 kilograms times meters per second. Now this problem asked us to find the maximum force as well as the average force. So we know that average force, F average times change in time, is equal to our change in momentum. Therefore, using our delta P that we have up here and the delta T that we had from the graph, which was given as 0.6 milliseconds, which we need to convert to standard units, I have the average force times 0.0006 seconds equals negative 9 kilograms times meters per second. All right, doing our math here, we find that the average force is equal to negative 15,000 newtons. Now looking back at the graph, we can see that the average force, or the maximum force, occurs at half this time. So because of that, it's going to be double. The maximum force will be double that because you're dividing by half of the time. So the F max is equal to 30,000 newtons. Now the only reason that mine is negative and it appears positive, we can use the magnitude, is because I chose my initial direction to be positive and the final direction to be negative. So the magnitude of the force is what's displayed on the graph. Okay, so continuing on. All right. So the impulse approximation says that we can ignore any other forces. We're just focusing on the forces that are being identified in the problem. So generally things that we ignore like drag, air resistance can still be ignored in these types of problems. All right, so the Karch change in momentum of delta P. So take a minute, look at this quick check, and use the, make sure that you pay attention to the direction that the velocity arrows are indicating the object is moving in initially and finally, and then take a moment for this quick check. All right, so solving the quick check, we see that, here we go. Initially, the object is moving to the left at a -2 meters per second, and then at the end, it was moving to the right at 1 meter per second. So delta P, m, v final minus v initial. So I have delta P equals 10 kilogram cart times v final minus v initial, 1 minus a -2 meters per second. All right, so 1 minus a -2 is just 1 plus 2. All right, so we end up with a change in momentum of 30 kilograms times meters per second. All right, so hopefully you found that answer 2 in the quick check to be E. All right, and then our one of our next example problems, we have a 500 kilogram rocket sled is coasting at 20 meters per second, and then it turns on its rocket engines for 5 seconds with a thrust of 1,000 newtons. What is its final speed? Okay, so the same idea here. I know that my mass is 500 kilograms. Thrust is an example of force, so my force in this case is 1,000 newtons. The time period over which the force was applied was 5 seconds. And I also know that my initial velocity, v initial, was 20 meters per second. Okay, so I want to know what is the velocity after this thrust has been applied. So I'm going to say F delta T equals delta P, which is m v final minus v initial. So my force here is 1,000 newtons times 5 seconds equals 500 kilograms times v final minus 20 meters per second. All right, so I do my math, solving for v final, and I find the final velocity to be 30 meters per second. All right, sorry I didn't put that on full screen, but you can check it out here. All right, so using the impulse momentum theorem, you guys have had some great examples of it so far. Want you to try the last example in this section on your own, and we will go over it, or I'll post some solutions online so that you can check it out. If you guys have any questions, just make note of them in your notebook and we can go over them when I get back, but hopefully this gives you a little bit of a better understanding of how to use this theorem in different types of problems.